Hello class, this is your part 1 lecture for geodatabase topology. Part 2 is actually in a PowerPoint format, but it is for your reading and reference only. So this will be the only video that you need to listen to in reference to the lecture. However, you'll notice in the first activity that there is another video to watch that introduces you to working with some Esri resources in determining which topology rules to choose for your data. All right, so moving right ahead, first thing we need to remind ourselves is why are we even talking about topology? Why is it important that Esri brought back this concept of topology back to the GIS data model? So from your readings, this should already be swimming through your head. So you should have some answers available for this question. And we're just going to see a few of them zoom in here. So if you have a question of whether or not your data is clean or is actually looking and functioning the way you want it, how do you answer that question? How do you put your data through a set of tools or rules to find out if your data is actually built the way that you want it to be built? How do you know if features that are supposed to be adjacent or are supposed to be coincident or sharing space are actually sharing space? You can only zoom in so far, and you can only do that so much across your data set. Is there a way that we could actually do that and know and have confidence in our data? How do you know if there's editing artifacts? What if after a whole bunch of editing and deleting, you want to know if you have tiny little lines or tiny little polygons floating around out in space and you don't want to have to dive through 1,000 records in your table? How would you identify those? So basically what this all comes down to is this concept of data integrity, making sure that your data is actually built and working the way that you assume that it's built and working for the tools and analyses that you'll be using on that data. And really this all lands on being able to use our data to model the real world, which is really what we're doing with the world of GIS, is we're using data to model what's happening in the real world. And the real world is built upon a set of rules. So we need to have a way for our data to do that as well. So let's talk about what topology looks like in the geodatabase model. For geodatabases, the topology system now is a set of rules that define how our points, lines, and polygons are going to interact. So rules can be established in two different ways. They can establish to look at how features within a single feature class are behaving, or they can be used to look at how multiple feature classes are behaving together. Some examples usually help drive home this point. So for within a single feature class, we know that roads out in the real world should not overlap themselves. We do not have two paved roads that are sharing the same space. There's a single road there. So it stands to reason that our GIS data shouldn't have any line features that are totally overlapping each other. So that's a rule we could set up. How do we identify if there are any lines in our roads GIS data that are overlapping? With multiple feature classes, we can think about roads again, and we can think about the concept of roads and bus routes. So our bus routes clearly always have to be roads, but not all roads are bus routes, but all bus routes are roads. So using that logic, we could set up a rule between those two feature classes saying that bus routes should always overlap completely with roads. So that's two very easy examples about how these rules can be used to look at your data. With the geodatabase topology model, we're modeling three primary relationships, and these relationships should look familiar because they were also the relationships that were modeled with the coverage data model. But the limitation of the coverage data model was that it only looked at mathematical topology. So you couldn't get beyond just the rules of how things were touching each other and sharing space to ask questions across data sets. So with the geodatabase topology rules, we get to kind of go even deeper and broader with these topology rules and examine some different relationships within and among data. Those three main topology relationships are adjacency, coincidence, and connectivity. Termed together, these are often termed as coincident geometry. And as we go through each of these, you're going to see, I will highlight for you what within each of these relationships is the actual coincident geometry with topology. All right, the first one we're going to look at is adjacency. And this is what lets you identify which features share a common boundary. So if something is adjacent or contiguous, it should be right next to each other. Now in the shapefile data model, when features were adjacent, those boundaries, that shared boundary was still stored twice. All right, so those polygons each were their own entities, and they had their own full suite of their outline of their perimeter, and that boundary was stored twice. And we had no way to ensure that that boundary was completely seamless. With the geodatabase topology, we have a way to say if two polygons are next to each other and we assume that they should be adjacent, then that their shared boundary, that boundary space that they both have, should be in the exact same place. So it's not like coverages where that boundary is stored only once and used by two polygons. The boundary is still stored twice, once with each polygon feature, but the software knows that the shared boundary should be in the exact same place. So we can ask questions about which landowners share a property line, which soil types are next to each other. It ensures that we're not going to have any gaps or overlaps between those two things that should be right next to each other. For adjacency, our coincident geometry is that shared boundary. That's what we're looking for that coincident geometry. Next up is coincidence. And this is features or parts of features that need to occupy the same space in the same plane. So we're usually thinking about 2D data here. And this goes back to our bus route and roads example. So our bus routes should always occupy the same space as our roads feature class. So our geodatabase would look for these coincident features, and these would be our coincident geometry. So the lines that are in both bus routes and roads would be our coincident geometry. Now, within GIS data, we have the ability to consider something coincident, even if it's not at the exact same precise point. And that's where we get into this concept of cluster tolerance. Cluster tolerance is very similar to the concept of XY tolerance. It is a distance within which things will be considered coincident. So what it means is that if you have data that may not be exactly in the same place, you can manage through your cluster tolerance and say that all features that are within this specified distance should all be considered coincident, should all be considered in the same space. Now, as we'll see, as we saw with XY tolerance, and as we'll see with cluster tolerance, this is a, by default, very, very small distance, because obviously we don't want to be looking out feet and meters and saying that things should be sharing the same space, because then you often get really, really messy results. But it is good to know that if you have data from different sources that were maybe done in a different production scheme, maybe they first started off in different coordinate systems and you've moved them to a common one, and they could be off by a fraction of an inch or a fraction of a meter, but still be representing the same thing, you as the GIS professional don't have to go in and make those microscopic changes. The software is set up to recognize things that are within a special distance of each other as actually being the same and sharing the same space. We will have more on cluster tolerance a little bit later. All right, so connectivity. This is what allows our features to connect together, to attach to each other. And this is how we model flow in our GIS data. So how do cars move across a network? How do things within water lines and valves move? So it's very important to know how to follow a path between a wastewater treatment plant and a house, right? You want to model that in the right direction. You want things to be moving away from the house to the wastewater treatment plant, not the opposite direction. So you want to be able to manage your data and how it connects at these lines and endpoints, that your lines are in the correct direction and the correct lines connect at the correct points. Similar out in the natural world with streams, this is what allows us to model stream flow in a particular direction. So with connectivity, our coincident geometry are those shared endpoints. That's how we connect features up and allow things to move from one line to the next line. All right, so now we're going to circle back to our concept that we started with at the beginning of these slides, which is why topology. So we talked about it in generalities about why it's good that it brought back. So this is a little bit more specific in that topology is what we need to maintain our data spatial integrity. So it can be used to ensure that our lines intersect properly, we don't have overshoots and undershoots, and it can be used to ensure that our polygons properly share boundaries, so eliminating our sliver polygons or our gaps between polygons. For existing data, it's what ensures the ongoing existing structure of our data. And if that data is meeting the rules of planar topology, it's what helps us maintain it. Because once you have a topology, you can edit your data such that it belongs and it pays attention to those topology rules. So for existing data that's already good, it helps us ensure the existing structure. For new data, it's going to ensure the quality of our new features. It's going to ensure that when we build new data, it's going to adhere to those rules. And if our rules are the planar topology rules of no overlaps, no gaps, etc., then it's going to ensure that. But it's going to ensure that our topology rules are adhered to as we move forward and create new data. All right, so this is what's necessary for modeling our real-world interactions. So let's talk about the general procedure for doing this. So first I'm going to look at this in just regular words. So the process in general is you determine the rules you want your data to follow. You're going to use the computer to check your data to see if it follows the rules you have set up. You're then going to look at the places where the rules have been broken, and then you're going to recheck to make sure that your fixes, so you'll look at the places where the rules are broken, perhaps try to fix them, and then recheck to make sure that those fixes worked and didn't cause any other errors. So that's in like human terms what we're doing. Specific to the topology process, this is what this looks like. We create the topology, we validate the topology. So validating is what's going to look at those rules and apply those rules to our data and see if they follow the rules. Once we get the results from our validation, maybe we're going to need to fix some of our topology errors, and we're going to talk about how you do that. And then once you do those fixes, you've changed the data, so you need to cycle back and revalidate your topology. So this is the general workflow that we work through when we are working with topology in the Esri software. So let's talk about how we do each of these things. So how do we create topology? Well, it's done in catalog within your existing geodatabase. Remember, topologies can only exist in feature data sets because that's the place where you're making sure that all of your data is in the same spatial reference, because we can't compare coincident geometry between two data sets that are in different coordinate systems. They have to be in the same coordinate system. So that is the reason that this all has to be within a feature data set. So you would create your topology within your feature data set. When it's created, it does store a set of properties and special topology features. The properties it stores that you are going to interact with are the cluster tolerance, the ranks, and the rules. And then the special topology features that will end up being created are dirty areas, errors, and exceptions. And we're going to talk through each of these properties and each of these special features. Up first is our cluster tolerance, which I alluded to before. So the cluster tolerance is the distance in which all geometry is considered identical or coincident. In the software, the default or the minimum is 0.001 meters, or whatever the units are of your coordinate system. That's the default. The cluster tolerance now actually takes from the XY tolerance that you've set up for your geodatabase feature data set. So whatever you set there will be the default for your cluster tolerance. Again, what I want to drive home here is that this is a very small distance. So here's what happens with this cluster tolerance. So pretend that you have these two lines in a data set, and you are putting them through the validation process of topology. The process is going to see, because these two endpoints fall within this very small cluster tolerance, it's going to see them as coincident. And what's going to happen in the validation process is that it's going to move them to a common point. It is so that they do actually share the same space. This is just making your data cleaner. It's not changing your data in a tremendous form because it's not a big distance. But you do want to be aware that this is sometimes happening in the background. But that's why that cluster tolerance is set to be so small, because changes in that amount of distance shouldn't affect your data. All right, the next topology property we're going to talk about are ranks. So when you go to build the topology with the topology wizard, you get to tell it what data sets you want to have be within the topology. Each time you choose a new data set, you get to say what you want its rank to be. And the ranks are a way for you to determine if there's more important or more valid data that you're going to be including in your topology. More often than not, all of the ranks for every data set that you put into a topology are all left to be 1, an equal ranking. Every data set you think maybe comes from the same source, it's your same organization, and all of the data should have an equal rank. An example of a situation where you might want to have different ranks would be if you had parcel data that was created from a very detailed plat map. The auditor's office had spent a lot of time making sure that that data was as accurate as possible. But then you had zoning polygons from, let's say, a township or the county that were hand digitized and had not gone through the same rigorous process as your parcel data. If you are going to ask a question or set up a rule that's saying all of your zoning polygons should include, should never break a parcel boundary. So all parcels, the whole parcel, should be within one and only one zoning polygon. You might have situations where in that cluster tolerance, their boundaries are slightly off. Now, if you have a really authoritative data set like the parcels and a somewhat non-authoritative data set like the zoning polygons, you don't ever want your parcels to move towards your zoning polygons. Keep in mind, it's still that tiny little distance. You would always want your less authoritative data set to move within that cluster tolerance distance towards your authoritative data set. So in this example, we would set up our parcel data to be a rank of 1, our zoning polygons to be a rank of 2. That way, when anything would be going through this process and adjusting within that cluster tolerance distance, our lower ranked features are always going to move within that tiny cluster tolerance distance to be matched up with our higher ranked feature classes. For this class, we will always keep a rank of 1. There's very few situations where you actually end up using these ranks, but they do become important, like the scenario I just mentioned. So I want you to know that they exist and why they exist, but just know for class, we're going to stick with everything having an equal rank of 1. All right, so now let's talk about our topology states. So when you go through the process of topology, you're going to have your topology, when you look at the properties, it's going to report out one of 3 states, either not validated, validated errors exist, or validated no errors. When you are not valid, it means that dirty areas exist. And in the next slide, we'll talk exactly what a dirty area is. But a topology is in this state is if it has not been validated after you created the topology, meaning that your data has not been evaluated against the rules, or if edits are made to any of the data that participate in the topology, and after those edits have been saved, you didn't revalidate to check those edits against your topology rules. So that's what not validated means. When you have validated errors exist, it means that whoever created the topology or is working with it went through the validation process. The software went and looked at all of the rules, evaluated against all the data sets, but you have some errors. Now, errors just simply mean that your data is not following the letter of the law with the rule. So as we talk through this and work through this in class, you're going to see that sometimes errors are just the way the data is. But this is finding every place that your data breaks the rules that have been set up. And in general terms, we call those errors. So we also might see that validated no errors, meaning you've validated your data against the rules and all of the dirty areas have been checked and no errors were found. So that's the 3 different states that you'll be able to see in those properties. All right, so let's talk about that special feature, that dirty area. Dirty areas are simply places where your data has not been evaluated against the rules. So the data has not been validated against the rules. So this can contain existing or undiscovered topology errors. When you first create topology, the first time around, your entire study area around all of the data that participate in the topology is going to be marked off as a dirty area. And we'll actually be able to see, you can turn on a graphic that shows you the dirty area within the spatial features that you're working with. It'll be a giant square polygon. So after you do your validation and after you do your checking and you look at your rules, after you're finished with that, you'll notice that your dirty area no longer exists. All right, but if you were to do any edits along the way with either fixing some rules or your data just needs updating after the fact, you'll notice that small little dirty areas show up. This is a way for the software to be most efficient during the validation process. So the first time you validate, everything gets validated and evaluated against those rules. And sometimes that can take a couple of hours to happen. Moving on, The way that the software and the engineers decided to say, okay, we don't need to put everything through. We just need to be able to highlight the places where there have been changes since the last validation. These dirty areas are used to identify areas in your data sets that have had edits done, and these areas no longer can say that they've been evaluated in their current state against the rules. So that's why that's the concept of dirty areas. So what it does is it makes your validation moving forward much faster, and it's a way for you to be efficient during your editing. All right, so let's talk about those topology errors. How do we see them? What do they look like? So when a rule is violated, it's assumed that it's an error, but as we'll see as we move forward, sometimes not all errors mean that it's wrong in the real world. But if an error is detected, what happens is that an error feature is created, and this is just a smart graphic. So what happens is that you'll notice in your contents, you'll have some additional some additional features show up that are these shapes. So if an error shape of a point appears, so let's say that we had a rule that said point must be inside of polygon. And if we have a data set of addresses and a data set of parcels, so we know that an address point should be inside the parcel. Well, if there's an address point that's floating around and not inside a parcel, that point is going to have a red graphic drawn on top of it. And that's going to be how you drive to that error and how you visually see that the error is there. So for errors that occur with line rules and line data sets, you're going to see an error shape of a red line. And for errors that are associated with polygons, you're going to see a polygon shape identifying where the error is. And we're going to get lots of practice with this in our activities about seeing those error shapes and understanding how they can be used to help us fix our data. All right, so how do we manage these topology errors? It's great that we know how to create the rules, generate any potential errors, but once you find them, what do you do? Well, errors can't simply be deleted, or there's not just one giant fix button. You have to go through each individual error that's listed and manage them individually. Now, they have a couple of different options for managing them. First, you can just leave the errors in the geodatabase. I mean, sometimes just knowing the error is there is fine, but it's not affecting your data, but it just gets left. All right, and that's okay. Your data will still behave even if there's an error. The error is just a message to you that your data isn't following the rule that you say it should. But it will still go through the tools. It won't flag any errors in the tools. Just know that if your data is bad, it might not have the result that you want out of the geoprocessing tools. You can also fix the error using what's called the Fix Topology Error tool. So for each particular rule, there are a set of predefined possible fixes. You can kind of think of this as a right-click menu or as a spell check function in Windows. So it sees that you've made a mistake and it gives you a small list of things that it thinks that fix that mistake. These are not always the ones that you want to do, and honestly, not all rules even have a predefined topology fix. But you'll have resources that show you what those automatic topology fixes are, and it is often about right-clicking, select the fix, and then that method runs on your object. So this is a classic example of object-oriented programming in action. Your errors are their objects, the predefined fixes are the methods that can be used on those objects, and you choose the one that you think best fits, if one does. Now, that's using that automatic fix. You can also use all of your editing tools available to you to edit your feature classes. And sometimes that's what you simply need to do. You just need to get in and do some edits that make your data match up better with the rules. Finally, you could also mark the error as an exception. This gets done oftentimes with those errors that you might leave in the geodatabase just because they are okay and they are how your data is supposed to be. So you can mark it as an exception, and that just means that ArcPro is going to stop telling you about it repeatedly as you move forward. So let's look at this as a graphic. So what's the process of the topology creation and management of our topology rules throughout time as we do this? So the first thing we do is create the topology. And what goes into that are our data sets with our rules, our ranks, and our cluster tolerance. So those are the properties that go into our topology. So as soon as we put data into that topology and have our rules, we automatically create dirty areas. Remember, that first one is just a giant, big, dirty area. So in order to evaluate our data against the rules, we need to validate our topology. So when we validate our topology, we might end up with errors. All right, if we end up with errors, one workflow is to mark them as an exception. Another is to go through a process of fixing those errors. If we mark them as exceptions, those exceptions just live in our topology, they live in our geodatabase, and we just make the assumption that our data then is in a status of correct or some state that we're okay with. However, if we go through the fix process, every place we fix creates new dirty areas in specific locations that then need to be revalidated. So we're back into the validate topology loop of this model. All right, so as we go through here, we fix all of them, and if we don't have any errors, we can go directly to our data is in a state that we're fine with, data being correct. All right, so we might sit here for a while, but let's say your data needs an update. A new road gets done, or a road turns from a two-way to a one-way road, or somebody digs a new pond in your study area, so you need to digitize in a new pond. So that's a data edit. So that's your editing features. And as soon as you do that, you create dirty areas, which puts you back into this validation process. All right, so this is the loop that you're going to be in as you work in topology. This area down here in orange, this is what part 2 of this module really focuses on. This is looking at the different rules and their potential fixes. So the part 2 PowerPoint slides go through all of the individual rules within the Esri suite and talk about the different scenarios that they model and some of the potential fixes that you have on the outset of them. So make sure that you go back now to part 2. Part 2 will start off with this graphic and remind you of it. And then it will walk through all of the different rules that you have for point, line, and polygon data sets.